All right, let's take a look at what the derivative would look like if we're coming from data points. This is, of course, only an approximation because we can't get instantaneous rate of change, but we're going to try to use average rates of change to give us some idea of what the derivative of this function that's recorded in here might look like. And so what we have to do is we have to, first of all, come up with a rate of change and decide then where are we going to plot that rate of change. And so if we're using these as our first 2 points, then it makes sense maybe as a plotting to go halfway in between those, which would be negative 1.25. So if I use that as my x, or this is calling it a time, and negative time can make sense in some things. But then our rate of change, so which we'll do the average rate of change at that point, is going to be a change in y over change in x. So 0 minus 4.1 divided by that 0.5. 0 minus 4.1 is negative 4.1 divided by half is times 2. So that would be like a negative 8.2. Okay. That would give us an approximate value of the rate of change between those. And then if we just continue with that process, halfway between negative 1 and negative 0.5 is negative 0.75, and negative 2.1 minus 0 is negative 2.1 divided by a half is negative 4.2. And my next one, I'm kind of picking up a pattern because of the even spacing here. I got a negative 0.25 on that. Negative 2.5 minus negative 2.1 would be a negative 0.4 divided by a half is a negative 0.8. This would be a positive 0.25 there. And negative 1.7 minus negative 2.5 is like a 0.8. Divided by a half is a 1.6. Shifting the blue here again. This is a 0.75. And 0 minus negative 1.7 is a positive 1.7. Divided by half is a positive 3.4. This would be a 1.25, and 2.2 minus 0 is 2.2, divided by a half is 4.4. Lots of fun noises going on in the background. Shifting to the red, that gives us a 1.75. It's halfway between those. 4.5 minus 2.2 is 2.3, divided by a half is 4.6, and this would now be a 2.25, and 6.6 minus 4.5 is like 1.9, so divided by half would give us a 3.8, and a 2.75. And that's a 2.8, because what we get for that one. And then a 3.25, that's as far as we're going to be able to take this, because we run out of data at that point. And 0.4 divided by half is 0.8. And so these are our approximate values in there. I've already kind of loaded those up down here. And so this on the left is the graph of the original data points. And on the right over here, the approximate values of the derivative. I couldn't get this to overlay one over the top of the other. But you can kind of see where things are happening there. This one's down here at around -8, and just south of -4, and right in here somewhere, and just under 2. Get these approximately anyway, somewhere between the 3 and 4, and between the 3 and the 4. I didn't go up high enough on that one. So this next one up there, and then somewhere in there, and a little bit higher here, and then back down, and slowly working our way back down this direction. So you can see the original function, we kind of have a sense of it doing this kind of thing, and the derivative as we have approximated it doing this kind of thing. So that's how we can approximate values of derivative from a table using average rates of change to approximate our instantaneous rates of change.